Again, let's go through the journey. This is something is going to be in your test, to know about what is that four function, what are those four functions that you're going through step by step to build the exact accumulation function from the exact rate of change function. Briefly, let's go through and find out again what's the four functions you have to know. Exact rate of change function. From the exact rate of change function, we want to find out the exact accumulation, net accumulation function first. The exact net accumulation gives you what? Gives you the net change in the dependent variable, right? From an initial value till x. So what are the intermittent steps? You're finding out, oops, sorry, we have to, so the intermittent step, we have to build the approximate rate of change function using the left-hand approximation method. Using delta x intervals, divide the interval into certain number of subdivision, and we use the rate at each left-hand point. After that, from the approximate rate of change function, we build up the approximate accumulation function. How do we do that? How do we get from the exact rate, the approximate rate of change function to the approximate accumulation function? What do we do? Using what?
Delta x.
Using m times dx, right? Using the rate times m times the change in the independent variable, right? And we sum up the little changes, right? Okay? So consequently, the approximate net accumulation function is a piecewise linear function, right? And then we get the exact accumulation. How do we get the exact accumulation from the approximate accumulation? We delta x make it extremely small, very small, infinitely many small. Then you need to add up infinitely many infinitesimal terms, and then you use integral for that. Again, you're adding up the changes from a to x, so that's why you have to use a different variable for the integral. It doesn't have to be t, could be any other letter. All right, so again, one more time. We think of the integral as a sum. When delta x is small enough, it's so small that the accumulation to the current interval doesn't contribute to the accumulation anymore. And these are basically same formula. Both are summation. One sum is a finite sum. You're adding up finitely many terms. The other sum is an infinite sum of infinitesimal terms. You know you have the rate in both formulas, except the other formulas, the left-hand points and the right-hand points is already kind of converged together, right? Okay, so that's why we don't distinguish between left and right here, right? It's just one value between x and a and x, t. Then we find the accumulation. One is exact, the other one is approximate, but if delta x is very, very small, then there's no basic distinction between the two quantities. We're summing up, both are sum. One is an infinite sum, other one is you're adding finitely many terms. You're accumulating bits of changes in the dependent variable from the initial value a and the final value, which is the variable x. So both are functions. Okay? So think of them as basically very similar. One is finitely many terms, even if you have million, but it's still finite. The other one is an infinite sum of infinitesimal terms. So we're almost the end of our journey now. Again, just quickly, and we're going to have the final conclusion, what we call the fundamental theorem of calculus. So we have the final value, right? We have the exact rate of change function. I like to use this notation. It's just brief, the exact rate of change function. Next step is exact rate of change function. You construct the approximate rate of change function using the left-hand approximation method. This is the short formula, what you do. R of x, the approximate rate of change function, you evaluate the exact rate at the left-hand value of each delta x interval, right? That's what this is shortly. Or what you have that step function, that's the short notation for that. The approximate rate function is piecewise defined in each delta x interval. The graph of each piece is a horizontal line segment, right? Representing the constant rate, right? After that, we're building the approximate net accumulation function using, just referring to this as a quotation mark, the MDX formula. MDX formula, you remember when we had only constant rate state line, that gives you the change in the y, right? That gives you dy, right? So you're using many times, right? Many times. Depends on how many subdivisions you have, and you're adding it up. This is the total number of completed intervals, and then we have the little accumulation from the left, right? Whatever, the x is the current interval. So consequently, the graph of the approximate net accumulation function is as a piecewise defined function, and the graph is piecewise linear. Again, the approximate net accumulation function gives you the approximate net change in the dependent variable, how much the weight changed, how much the distance changed from the initial value, okay? This change is calculated many times as a bits of changes, right? All right, so the final value, the exact net accumulation function, how you get that? When that x shrinks to almost zero, never actually zero, but almost zero. Guys, would you put your phone down? And really, I don't want anybody to be in the phone at all. Okay, would you just put your phone away, okay? Right, so delta x shrinks at almost zero, not exactly zero, but close to zero, arbitrarily close to zero, and then the sum becomes an infinite sum of infinitesimal quantities. That's when we use integrals. Integral from a initial value to the variable x, and then you're still summing up bits of changes in the dependent variable. Rate, we don't distinguish between left and right anymore, just one value, and the change in the independent variable. So here is the big step here right now. The other way to express the exact net change, well, here's just one net, okay? Exact net change in the independent variable, what we have done at the beginning of the course. How can you express the net change using function? Final minus initial. That's the same as f of x minus f of a, exactly, right? That's what we call the fundamental theorem of calculus. If you have taken calculus, this is what you learn, right? Two ways, right? So one, you adding up bits of changes together here. The other way, you just calculate it as final minus initial. So think about it. Here we go. If you have, you're filling up a glass with water, right? And this is my final value, f of x. And this is my initial value, f of a. That's the change between, right? Okay, so this is the change between final minus initial. And the integral is filling this up glass like little portion, adding up or summing up little bit of changes, right? So that's two ways. You have the final value, this is final, minus initial. You calculate, or you have the formula for the same thing two different ways. So they have to be the same, right? Two ways, you have the formula, so same quantity. That's the net, gives you the net change. in the dependent variable, that gives you the net change in the dependent variable as well, right? F of x minus f of a, final minus initial, so they are the same. So this is actually huge. Now rearranging this equation, then you get f of x equals f of a plus the change. This is exactly, you recreated the function, right, f of x, from an initial value plus the change. We know how to do that when we had constant rate, right? When you had a linear function, you had an initial value, I give you the slope, then you could actually calculate f of a. You can write down the equation of the line, right? When it's linear, right? This was only one change, then you have m times x minus a here when you had a linear function. When it's not linear, but you know the rate of change exists, then you can recreate the function as well. Just that change here is going to be many changes together. You have to use that an integral formula to calculate that change, piece by piece. This is what you have done in pre-calculus class, the same thing. I give you an initial value on the line, right? I give you the slope, write the equation of the line, right? That was no problem. Everybody could do it. High school, that was so easy, right? You do the same thing here. I give you an initial value. I give you the rate function, which is not a constant rate at this time. It's just a rate function. I give you the rate function, and you recreated the function from it. But that change, okay, that's going to be more complicated. That change is an integral. The integral expresses the net change. And to find that change, you have to use the game of constant rates many, many, many times. Okay? So that's what we call the fundamental theorem of calculus. In most of the time in high school or many times they just give you the formula and that's what it is, and you don't really know what the meaning behind it. Okay? But that's exactly what you have done with line. I give you the initial value, give you the slope, create a line. Here I give you the initial value, give you the rate of change function, and give me the equation, give me the function, recreate the function value. All right, so one more thing before we work on the next worksheet. This is a nice school animation for the sender worksheet. On the left, you see the exact rate of change function and the approximate rate of change function. And here is the slider, and I'm going to shrink that to x to almost 0, right? First, look at the exact rate of change function and the approximate rate of change function on the left. So I'm going to change that to x to very, very small. So what happens? The horizontal lines, because delta x is really small, the horizontal lines is more frequent and frequent, right? So it's so frequent, right, then basically the approximate rate of change function is almost the same as the exact rate of change function. So you could think of the exact rate function as a little pieces of horizontal line segments, right, representing the constant rates in that moment, right? Look at that, what happens on the approximate net accumulation and the exact net accumulation, right? So this is the approximate with delta x equals 0.3. And I make delta x to make it smaller. And look at that, the linear line segments, it smooths out and approaching converges to the exact net accumulation function, like that. Here we go. So this is how you visualize it, okay? How you visualize this shrinking, the delta S shrinking to 0. Never actually 0, but arbitrarily close to 0. So actually here even you can see delta X is still 0.005. But it's pre-exact now, at least visually to us, right? Okay. So what is exact enough? It depends on the problem. Obviously, if you're in chemistry, biology, extremely small quantities, you're dealing with extremely small quantities, then you have to decide what is a good approximation for you. You have to solve it with a computational device. Okay, what is good enough? What is the small enough, which is a good enough gives you a good enough approximation. All right. All right. So now let's work on our next worksheet.